Have you ever really stopped to think about how, well, anything gets made? A skyscraper, your phone, even the chair you're sitting in? They all start as just an idea, right? But how do they become real? Well, it all comes down to a kind of hidden language, a universal code for building our world. Today, we're going to decode that language. We're diving into the basics of technical drawing. See, at its very core, technical drawing solves one massive puzzle. How in the world do you take something complex, something three-dimensional, and squash it onto a flat two-dimensional surface without losing any of the important information? That's the big question. So here's our game plan. First, we're going to tackle how to get our 3D world onto a 2D plane. Then, we'll get into the nitty-gritty of drawing perfect curves. After that, we'll learn how to, see inside solid objects. And to wrap it all up, we'll use everything we've learned to read a real-deal architectural blueprint. All right, first things first. Let's tackle that huge, foundational problem, getting 3 dimensions down to 2. The whole mission here, the entire point of technical drawing, is to create a graphical representation of a 3D object that is crystal clear. We're talking zero ambiguity. This is an art class where you can have your own interpretation. Nope, this is pure, raw, unfiltered information.
So how do they do it?
Well, the secret sauce is something called the theory of projection. You can almost think of it like tracing an object's shadow, but, with way more mathematical precision. We're systematically taking points on an object and projecting them onto a flat plane to create a perfectly accurate view. And the most common, the real workhorse of this whole system, is orthographic projection. Just imagine you're looking at an object from a perfectly straight-on angle, first from the top, then the front, then the side. You put those 3 2D views together, and suddenly you have a complete, totally distortion-free picture of the 3D object. Okay, so now we know how to project things. Let's talk about the actual building blocks. Because if technical drawing is a language, then these basic geometric shapes, they're the alphabet. Let's take the ellipse, for example. It looks simple enough, right? An oval. But in technical drawing, there's absolutely no room for good enough. You need methods to draw it perfectly, every single time. We're going to look at 2 of the most popular, the concentric circle method, which is great for perfect symmetry, and the parallelogram method, which is a lifesaver for fitting curves into weird angled spaces. The concentric circle method is just a beautiful example of the logic here. You use 2 circles to guide you, you project a few lines, and the points where they cross literally map out your perfect ellipse. It's basically connect the dots for engineers, and the result is a flawless curve. But hey, what if your ellipse has to fit inside a tilted shape? Like on some angled part of a machine? That is the absolute genius of the parallelogram method. It lets you build a perfect ellipse inside any 4-sided shape, which makes it an incredibly powerful tool for really complex designs. All right, we've got our building blocks. Now let's go from flat shapes to actual solid objects. And to really understand something, sometimes you have to see what's on the inside. So let's start slicing things up. Okay, get ready for your new favorite word, frustum. I know it sounds a little weird, but it's super simple. Imagine you have a pyramid, and you just slice the top off. But, and this is key, the slice has to be perfectly parallel to the bottom. The chunky part that's left over, that's a frustum. That's it. So here you can see what I'm talking about. We've got our original pyramid shape, and then the part that's left after the slice is our frustum. And I promise you, now that you know what to look for, you are going to start seeing this shape everywhere. I'm talking lampshades, traffic cones, the bottom of a coffee cup, everywhere. But what if the cut isn't perfectly parallel? What if the slice comes in at an angle? Well, then you get what's called a truncated solid. That's the only difference. A parallel, level slice gives you a frustum. An angled, inclined slice gives you a truncated solid. It's all about the angle of that cut. Okay, this is where it all starts to click. Let's actually build the 2D views of a frustum, step by step, using the same ideas we've been talking about. Let's do it. So, first things first, you can't describe a cut if you don't have the original object drawn, right? So we start with our basic views of the full pyramid. Looking down from the top, we see a square. Looking from the front, we see a triangle. These are our starting points. Next up, we bring in the cutting plane. This line that we're drawing on the front view, that's our instruction. It's telling us exactly where that slice is going to happen. In this case, it's perfectly parallel to the base. Now for the really cool part. This is the crucial move. We take the points where our cutting plane hits the edges of the pyramid, and we project those points straight down to our top view. This is literally how we transfer the information about the cut from one view to the other. And there it is. We just connect those new points in the top view and we've created a new, smaller square. What we're looking at now are the finished, totally accurate top and front views of our frustum. We just described a sliced 3D object using only 2D drawings. How cool is that? So, we've talked projection, we've talked curves, we've talked slicing things up. For this last part, let's put it all together and see this language in action on a real architectural drawing. Okay, so when you look at a floor plan and you see a big, bold line like this with arrows on it, that is not a mistake. That's our old friend, the cutting plane. It's basically a note from the architect that says, hey, imagine you took a giant saw, sliced the building right here, and are looking in the direction of these arrows. This is what you'd see. And this is the aha moment. On the left, you've got the floor plan with that cutting plane line, and that one little line is responsible for generating this entire super detailed drawing on the right. This is a cross-section of the building. We can see its guts, the foundation, the walls, the floors, the roof, all of it revealed because we know how to read that cut. It's like having architectural X-ray vision.
So, let's just boil it all down real quick. Projection is what lets us turn big 3D ideas into 2D plans. Geometric methods give us the tools to draw every little part with absolute precision. Cutting planes, they give us that X-ray vision to see inside things. And when you put it all together, these principles create the language that lets us design and build our entire world.
So the next time you look at a building, or a cool piece of furniture, or even just some gadget, remember the hidden language of lines and views that brought it into existence. Now that you know the basics, you're in on the secret. So, what secrets are you going to find hiding in the blueprints of the world around you?